Section 4.2 is going to continue our discussion of divisibility. That's really what Chapter 4 is all about, is about divisibility. And in particular, we're going to look at two specific types of numbers, prime numbers and composite numbers. So let's first define what we mean so that we're all talking about the same thing when we say these words. A prime number is any positive integer with exactly two distinct positive divisors. I'll go through this whole list and then we'll go back and we'll give some examples. So if you want to leave yourself a little bit of space, if you're writing things out and without my notes, do that. Composite is any positive integer with more than two distinct positive divisors. A factorization is any expression of a number in factored form. And a prime factorization is a factorization containing only prime numbers. Okay, so let's go back up to the top of my list. Can you give me an example of a prime number? 2. And the reason 2 is a prime number is because it has two distinct factors, 2 and 1. And no more. Another one. 3.
1.
Factors of 3 and 1, right? 7. 7 and 1. And of course we have big numbers too, right? And it's not that this is huge, but it's certainly larger. 43. Right? Every now and then you'll hear in like pop culture kind of things of somebody discovering the new largest prime number known. I'm not interested in looking for any. But there really are very, very large prime numbers. Notice all the prime numbers I've written down are odd except the number 2. And that has to be true. Why?
Because after that, all even numbers are divided by 2.
Right. Any even numbers bigger than 2 would have 2 as a factor, right? So it can't have any other even numbers besides 2 itself. How about some composite numbers? Can you give me a couple? 4. Okay. 8. 10. Are there any that aren't even? 9. That's one. That's not even. It's in my list. 15. Okay. Lots of numbers. Okay, 21 and I'll stop. We could do this all day, right? Yep. We could write numbers all day and put them in these two categories. There is a number that I'm not putting anywhere. 0 is one of them, but we're only working with numbers that are bigger than, that are whole numbers, that are natural numbers. So 0 gets exempt from that reason. The number is 1. 1 is actually a counting number or a natural number, but it doesn't get included. Why does it not get included in either list?
Because it's 1 times 1. It's 2 times itself.
Yeah, it's this phrasing that is used here. It says exactly 2 and more than 2, right? And the number 1 has what factor? Just 1. And so this exactly 2 and more than 2 wouldn't fit. It doesn't fit in either of the descriptions. And we're actually talk about why we don't want it to either. Every now and then, in fact, I was interested to see if my other class, most of whom have had this class, they had a question talking about a die, and it talked about the prime numbers on a die. And I was really waiting for somebody to say, well, what about the number 1? Why didn't you count the number 1 as a prime number? But nobody did, so that's really good. Maybe they took this away, that 1 doesn't count. I'm not sure, but yeah. So 1 doesn't count, and there is a really good reason why we don't want it to, and we'll get to that later in this lesson. Factorization. So factorization is any factored version. For example, I'm going to show you the difference between factorization and prime factorization. The number 12 can be factored into 2 times 6. That would be a factorization for 12. Okay. But it's not a prime factorization. How come? Yeah, the number 6 is a composite number, right? Yeah, one of those numbers, namely the number 6, is not prime. So if we wanted the prime factorization for the number 12, any idea what it might be?
2 times 2 times 6.
2 times 2 times 3, yeah. We'd actually have to take that 6 and we'd have to break it down into primes, namely 2 and 3, and that would be the prime factorization for the number 12. Another way that you'll sometimes see this prime factorization for the same one looking is they'll write it as 2 squared times 3. Sort of shorthand, and that would be appropriate.
This is just a side note.
What's that?
Is the reason why one isn't...
Shh.
Okay. Sorry.
Yes, it is, Valerie. We'll get there, but yes, it is. Okay. No, everybody's like, what happened? Just hold tight.
I'm sorry.
I promise. I promise we'll get there. All right. She's trying to just steal the show. You guys saw that, right? Absolutely.
I'm so sorry.
No, that's fantastic. I'm glad you realized it. Yeah, we'll talk about that one. Okay, we're going to talk about 2 different ways to do prime factorization. I'm sure that there are probably other ways. One of them is a factor tree. Have you guys seen factor trees before? That's usually the one people have seen before. I'm actually going to show you another option as well, and it has pros and cons. I mean, both of them have pros and cons. So let's actually start with the factor tree because a lot of you are like, yeah, I know what that is. Okay. One of the pros of a factor tree is you can look at the number and you can divide it by anything that divides it. Anything at all. It doesn't have to be a prime number. Any number would work. And in particular, this one very nicely divides by what number? 10. 10's probably your best because it ends in a 0, right? And so we kind of try to divide it by something we see that's a little bit bigger. So it divides by 10, and then I would get 2366. Everybody good so far?
Yeah.
Okay, and I'm going to keep continuing to divide whatever results I have until I have primes. So for example, on the 10, I've got 2 and 5, and I'm done at the end of that because 2 and 5 are both prime numbers. I need now another number that divides 2366. 2. Okay. It's even. We know it divides by 2. So what is 2366 divided by 2? 1 something. 1 something. What's next?
8-3?
8-3. It's 8-3. 1183. And you're welcome to grab your calculators as you're doing this if you haven't already got them out yet. So 2's prime, so that's good. So 1183 is where I am. Now in theory, 1183 could be prime. It's certainly not even anymore, right? So we can't divide it by 2 anymore. Is there anything else that we'll divide by? Okay, it doesn't divide by 3. Does it divide by 5? Nope. And I only need to look at odds, right? I mean, there's no reason to, in fact, I only need to look at primes. I have to anyway, but there's no reason to test anything that's even. It's not going to work because it's not dividing by 2. 7 will work. 7 and what? 169 is it, Emma? Good. And then 169 might be a number that you're familiar with. Yeah, it's 13 squared, so it divides by 13 times 13. Okay, so this is the factor tree on this one. It's not too bad as far as factor trees go. One of the drawbacks, maybe the cons, if you will, of factor trees is that if your handwriting's not as neat as mine, you might lose the end of a branch along the way. It's easy to do. It's easy to do even if you do have neat handwriting if your branches get too massive or too condensed in a small amount of space. So one of my recommendations when you're doing factor trees is when you get to the end of a branch, I didn't do it because I wanted to show you now, but when you get to the end of the branch and you get that prime number, is to circle it. So when you go back to look at what your prime factors are, you didn't lose anything because you already circled it, sort of to draw yourself attention to it. Or you're welcome to use colors. I'm obviously using red, highlighters, things like that would be a possible way of dealing with that. So all of those right there are my prime numbers. And if I were writing out my prime factorization, then typically speaking, people start with the smallest one first. It's not wrong if you don't. It's just kind of standard. And you count how many 2's you have. So how many 2's are there?
2.
There's 2. So if you want to write 2 times 2, that's fine. I'm going to go with squaring. So 2 squared. What's my next smallest number? 5. How many of them are there?
1.
There's just 1, so I'm just going to leave it as 5. If you want to write 5 to the first, you could do that. What's the next smallest number?
7.
7. How many of those are there? 1. And the next number?
13.
Is it 13? And how many of those are there?
Squared.
2. It's squared, yeah. How could you make sure that you didn't lose anything along the way?
Check and see if there's any circles.
What's that?
Multiply.
You could multiply it back out. You could check that too. You're not wrong. It's just, yeah. But the nice thing at the very end is if you multiply this all back out, what should it equal? 23,660, right? I mean, like, that's the whole point, is that it's supposed to be the factorization for that value. Yeah. Okay. So is there any, just out of curiosity, did anybody not do factor trees before? This is the first time maybe you've seen them. No? Okay. Usually I have a couple people where they didn't do it with factor trees and they did it this other way. So let me show you another way. Factor trees are fine. They feel to me like in English when you learn about, like before you do rough drafts of essays and you do sort of like these brainstorming with bubbles. That's what that feels like. What'd you call it?
A brain web.
A brain web. That's what it feels like. So that's to me what this sort of feels like with math. The other method that I'm going to show you feels more like what you would do when you do an outline when you're writing. And so what we're going to do is we're going to start with the number 23,660. And we are going to divide, but it's going to look like an upside down division, by the smallest prime number that divides it. So what is the smallest prime number that divides this? 2. Okay, and we're not going to have any remainders, so I don't have to worry about remainders. I mean, that's the whole point. If I did a remainder, then I wouldn't have put the 2 on the outside. So what do I get when I divide 23,660 by 2? Yeah, 11,000 actually, 830, right? 11830.
Oh, I see.
Okay. What's next?
Divided by 2 again.
Yeah, it's still even, so I would just divide it by 2 again. So if I divide 11,830 by 2 again, what do I get? Five something, right? Because 5,915 is it. Good job, Emily. Okay, does it divide by 2 again?
No, it's
No. And then we check 3. Does it divide by 3? Nope, it doesn't. So what's the next number after 3 that's prime? 5. Definitely divides by 5 because it ends in a 5. So if I divide 5,915 by 5, what do I get? 1,183. That's a familiar number. We've seen that before today, right? You betcha. Does it divide by 5 again? No. See, and I don't have to go back and look at 2s and 3s. I already did all that. It's never going to divide by something smaller than the last number I divided by because I'm going in order. So does it divide by 5? No. So the next prime number would be 7. And if we check that one, it actually works. That's when I got my 169 earlier. Of course, that's sort of like cheating because we already did this once before. But you get the idea. And of course, you'd get your 13 and your 13. So, some pros to this. It takes less space. All the numbers are in the same location. They're not at different varying ends of branches. I like the fact that they're in order. I meant to do a highlighter. Let's try that again. Right? All the answers, all the division factors, right? The prime factors are all right there in order. So those are some things. It definitely requires you to do things in order for it to work out conveniently, right? Like I couldn't start at the beginning and say, I'm going to divide by 10. It doesn't work if you do that. You really have to go in order, smallest first, all that good stuff. So it's definitely got more structure and limitations in terms of what you can do and in what order. So if you're a free spirit, you might not like this. If you like the organization and structure, maybe you do. Either way, of course, you end up with the same answer. It's 2 squared times 5 times 7 times 13 squared. Okay, everybody good? All right. That's the only one that I'm showing you like that because I think that you guys can probably handle that because I'm going to show you something different next, okay? Every time I do a question like this on a test, there's going to be at least somebody who thinks, I'm going to multiply this all out. And sometimes it's okay, and the number's small enough that you can still manage it, and sometimes it's not. If you try to multiply this out, it's going to be a very large number, all right? And you're kind of being counterproductive. If the whole goal is to figure out what it is in primes, why would I want to multiply that out first? Are you with me? I'm sort of moving in the wrong direction. So instead of working on this in terms of making it bigger and then condensing it down, what we could actually do is we can condense down what we already have. For example, what I'm going to look at is just, the number 16 itself. Ignore all the rest of the pieces for now. Let's just talk about 16. All right, so maybe you decide, I like those tree diagrams. 16, let's break it apart. What would 16 divide very nicely into? 4 and 4, or 2 and 8, you bet. And then the 4 and 4, the 2 and 8 eventually will break down, and you end up getting how many 2s? 4 2s. This is 2 to the 4th. Is everybody good with that? Okay, great. Let's do the next one, the 81, but let's do it with the other way that I did it, okay? So let's do 81. What is the smallest prime number that 81 divides by? 9's not prime?
Yeah.
3. 3 will work. What is 81 divided by 3? 27 is right. What prime number will 27 divide by?
3.
3 again, giving me a 9, which divides by 3 a couple more times. So I end up getting how many 3s?
4.
Happens to be 4 again this time. It's not really because I structured it that way. It just happened to be that way, okay? The last one is 6. You can probably do 6 pretty easily. 6 is what? 2 times 3. Okay, so like that's great, but obviously there's got to be more to it because I've just got the work all smattered around everywhere. I don't have a final answer yet, right? Okay, so let me actually write this out a little bit bigger because my work is too small. So this is 16 to the 4th, 81 to the 4th, and then 6 to the 6th. All right, cool. 16, just the 16 itself, we said was 2 to the 4th. But then there's still this 4 here that has to be represented as a power 4. Is everybody good with that? It's okay? 16 is 2 to the 4th, and it happens to be raised to the power 4. 81 is actually 3 to the 4th, and it also happens to be raised to the power 4. And then 6 is 2 times 3 raised to the power 6. Now, we did a section back, I think it was in 3.4, where we had exponents. Do you remember working through some exponent stuff in that section? That's what we're able to apply at this point, those properties of exponents. So when I have a power to a power like this, so 2 to the 4th to the 4th, what can I do with those 4s? I can multiply them. So this is 2 to the 16th. So if that's what I would do to that one, I would do it to the next one too, right? So 3 to the 16th. What about 2 times 3 to the 6th? What do I do to use, what properties can I use to simplify that? Yeah, it looks like distribution, right? So I would have, this 6 distributing as a power to each of those. So I have 2 to the 6th and 3 to the 6th. Is everybody good with that? Yeah, and then there's some bases that match, right? So this base and this base are both 2's. So I have 2 to the 16th and I have 2 to the 6th. And Valerie just told me I can add those exponents. Does that sound good to everybody? Okay. So I have 2 to the 22nd. And then I can do the same thing to the 3's. I have 3 to the 16th and 3 to the 6th. And if I add those exponents, that is, I get 3 to the 22nd. Okay. So we're always trying to break things down into primes. We really don't want to multiply them back out. It will get very, very, powers of 22, your calculator might not even be able to tolerate it. It might spit back out at you something that's in scientific notation, and now you're stuck in terms of being able to work with it for what we're doing, yeah. Okay, C is different yet. What is different about C? It's adding things together. Okay, well, we didn't add anything together in the last 2 problems, right? There was no addition going on. So what do we do differently when it's addition? Well, we're still looking at, but the beautiful thing is, maybe I should pause for a second. The beautiful thing is, do you see all the primes? They're really good. I have a 2, I have a 3, I have a 7. They're already primed. So I really don't want to multiply this out. And really, power 55, I probably can't. It's probably not even an option, okay? So maybe with the 22 powers I could have in the last problem, but 55s, there's no way. So what can I do? Well, what I can do is I can look for things that they have in common. So notice what they have in common first. They both have 2 as a base, right? And they both have a 3 as a base. And they both have a 7 as a base. Okay, is everybody good so far? So what we're wanting to know is how many do they have in common? Well, they don't just have a 2 in common. How many 2s do they have in common? There's 6 total, but do they have 6 in common? They have a 2 in common, right? There are 2 2s here, and there are 4 2s here. So like if I wrote this out, I'd have 2 times 2 in the first one, a bunch of other stuff, and I'd have 2 times 2 times 2 times 2 in the second one. They'd have 2 2s in common. Everybody good with that so far? So I'm going to pull out, factor out 2 squared, because they have 2 2s in common. We'll deal with what they don't have in common in a moment. Right now I'm just looking for the pieces they have in common. How many 3s do they have in common? They have 4. The first one has 5 3s, the second one has 4 3s, so they both have at least 4 3s. And how many 7s do they have in common? 55, like all of them, right? All of them. Okay, we have factored this out. It's like in algebra in high school. You've plucked out the things they have in common. So are these values that your students in elementary and middle grades maybe not this big? I mean, right? I get that, but you're not in elementary and middle school, right? I think you can deal with the bigger numbers, and it's okay. The process is still the same whether the numbers are large or small. So when I pull these values out, the question is what is left? Now, recognize that what's left will have a number plus a number. Nothing turns into 0 because factoring is like division, right? You can't divide things and get 0. So whatever I have left, there's going to be a blank space, a plus, and a blank space. And you need to fill you need to fill in the blanks here. Okay, this is fill in the blank. Okay. So let's take a look at the first value. I'm going to erase all my markings on them because it's all a mess now.
A quick question.
Yes, ma'am.
So whenever you're adding, do you take the smaller one of the 2 that are in
We'll get there. Yeah, we're getting there.
Thanks.
Okay, so let's do it piece by piece. All the 2s are now gone, right? They got all pulled out. Agreed with that? Everybody good with that? The 2s were all pulled out. Were all the 3s pulled out? No. 4 of the 3s were pulled out, which means how many 3s are left? 1 of them. So there is a 3 here. And the 7s were also all pulled out. Agreed? So there's no 7s left because I pulled everything out in front. Now let's do the second set. What about the 2s? Were they all pulled out? Nope. There's still 2 left. So there's still a 2 squared here, or you could put 2 times 2 if you wish. How about the 3s? All pulled out. And the 7s? All pulled out. Okay, you're still not finished because now you have inside the parentheses some work to clean up. What is 3 plus 2 squared? It's 7. So now I have 2 squared times 3, to the 4th, times 7 to the 55, times 7. What if it had said 10? Well, I'd have to factor the 10, right? I'd have to break it down. 7's prime, so that's really good. There is still one more thing to do, but 7's prime, that's good. So what do you think I might need to do to finish this problem up? Yeah, I have a 7 to the 55, and I have a 7 to the 1, so this is 7 to the 56. And that's where we're going to stop for today. It's a great stopping spot. All right, so homework from 4.1 will be due next time. We're about to do group work for this. 4.2, put on hold. We'll finish it next class period.